Before we move on to an example, I want to talk a little bit about how to figure out where a force is acting on an object. So our forces for these problems are still the same forces we've had in chapter 4, our different kinds of forces. And just like in that chapter, they're all going to follow particular rules about where they act on an object. So let's go through them kind of one by one. So it turns out friction we're not going to see in these kinds of problems, but if we were, friction would be acting at whatever surface is rubbing. Yeah, we're not going to see friction in torque problems, so don't worry too much about that. Okay, tension is going to be acting on our object wherever the string or rope is attached. And that's, of course, in the direction of the string. For our spring force, that is going to be exactly the same. It's wherever the spring is attached in the direction of the spring. So I'm just going to put ditto marks and just say spring instead. Normal force, so if we have objects pushing each other. Here, this could be a little tricky because if we have like two objects touching each other like this, there is, we could think of this normal force as being spread out over this whole surface, right? It turns out we're not going to worry, we're not going to have to worry too much about the size of objects, and we're just going to, all of our like object measurements like this are going to be relative to the center. So we're just going to say the normal force is like a single force acting at the center of that object. The center of the smaller object, not the center of this big table or whatever. Okay, the last one is gravity, which is actually the most important. These are all going to be pretty obvious. Like the tension is where the string is. The normal force is where the smaller object is. Gravity, gravity, if we're thinking about gravity on a large object, gravity is pulling on all parts of that object at once. So if I have my meter stick, we can think of each little segment of this meter stick is some little mass that has a little mg from gravity pulling it downward all at once. Now, of course, that is very inconvenient. And so it turns out it is mathematically the same to just treat gravity as if it is acting at a single point on that object, which is effectively like averaging together all of those little tiny mg's pulling down each part of it. So gravity is a single force equal to mg acting at a single point called the center of mass, which may have been a term, maybe a term that you've heard before. So the center of mass of an object is really just the average position of all of the mass in the object. So in real life, if we have some complicated object, some object with some complicated shape, figuring out where the center of mass is it's actually kind of a classic calculus problem. And for arbitrary shapes, it can be kind of hard to calculate exactly where that is. In general, if we have one side of something where there is more stuff, so let's make this a little more lopsided. We have some, I don't know, squash. This is shaped like a squash or something. The center of mass is going to be closer to this big side than it is to this small side, because this is where more of the mass is. So that's kind of how it works. In terms of what we're going to be doing with it in this class, there are two possible scenarios. One is we would be given the center of mass. So, in other words, here's some object. We're told, oh, the center of mass is 20 centimeters from this right end, and it's been marked with a dot on the diagram or something, something like that. Or we will be told the object is uniform. So one example of that would be our meter stick again. And so here's our meter stick, 1 meter long, and I can tell you exactly where the center of mass of this object is because it is marked. This thing is 100 centimeters long. The center of mass is marked with a 50, right? Because this is uniform. It's made of the same stuff. It's the same thickness. It's the same shape the whole way. And so the center of mass is going to be halfway between the two ends. It's in the middle of the object. And not coincidentally, that is also the point where our object balances with a single point of support. So in that case, if we have a uniform object, that means the center of mass is at the center of the object. And, if that's true, we would be told the size of the object, so you would know where to put that center of mass. So this might not be something you're given explicitly, but you might be told the object is uniform, and then you should know that the center of mass is in the middle of the object, halfway between the ends. Okay. Now we are ready for a real full-blown example. So this is our real static equilibrium example, and here we go. So let's say we have a seesaw or a teeter-totter or whatever people call them these days. And this is balancing at some point. The thing that levers or whatever like this balance on is called the fulcrum. Fulcrum, good vocabulary word. So on the seesaw, we have two boxes. There's box B and box A. And box B is 2 meters from the center, and box A is 0.8 meters from the center. And I should say the fulcrum is at the center of this board, of the seesaw board itself. So I guess if this is 2 meters long, this is also 2 meters long. But these numbers aren't going to matter except to show us that this is in the middle of this. Okay, we'll erase those. So. Moving on. So box B has a mass of 30 kilograms. I guess these are probably supposed to be people. I drew them as boxes. So person B, who is box shaped, has a mass of 30 kilograms. We would like to know what the mass of person A, who is also box shaped. And that is assuming that this is balanced. So, what is mass of person A if the system is balanced, or in other words, if our system is in static equilibrium, nothing is moving here, everything is just staying still and happy where it is. All right. So to start with, we should draw a free body diagram. So our steps for the free body diagram are to draw our object as a line. So there is the board of our seesaw that is feeling these forces on it. Now we treat all of our forces as acting at a single point on the diagram. Okay, so we have object A and B are both pushing down on this with some weight, right? So here we have force B. Somewhere over here, we have force A. In the middle, we have this fulcrum pushing up. Well, we don't need to know that yet. Hold on to that. Okay, if this board has some mass, its center of mass is right there in the middle because we're assuming this is uniform. And so at this point in the center, there is also some force of gravity pulling down on it. And now looking at this free body diagram, if we have three forces down, this thing is going to accelerate down and fall down. So we must be missing something, and that is the force from this fulcrum. So this is holding up this seesaw. If we, cut this off, the whole thing would fall down. So in other words, there's an upward force, like a normal force, from the fulcrum up at the center. Okay. So, if we treat this like a regular free body diagram, what we have is FA, FG, and FB down, and FN up. What this means is that the three weights, the force of gravity on A and B and the platform itself, have to be balanced by the fulcrum, or in other words, the fulcrum is going to feel the weight of those three things pushing down on it and is going to push back to keep them from falling. So that makes sense, right? The amount that this is going to feel is the weight of all the stuff above it. So that checks out, I guess. All right, but we want to actually find out how big MA is. That's our job here. So FB, we know, right? This is 30 times 9.8 newtons. That's 294 newtons of force. So this is 294. We don't know this, we don't know this, and we don't know this, and we want to find this out. So how can we do that? Well, it turns out we just need to make a good choice of rotation points when talking about our torque. So this is a torque problem. We want to be thinking about this in terms of torque. And we know that when we're adding up torques, we have to pick a single point to use as our center of rotation. And we know that if we are in equilibrium, if the system is balanced, the sum of our torques is equal to 0 for any rotation point, even if nothing is rotating, and in this case, definitely nothing is rotating. So here's the trick, and we will erase this. So our torque equation, when we sum up these torques, we're going to get something that looks like this. We're going to get a torque from A, we're going to get a torque from B, and we're going to get a torque from each of these normal force and a torque from gravity or something like that. Now, this one we know, this one we want, these two we totally don't care about. It would be nice if we could make them go away. And we can. And here's how. Our torque equation is RF perpendicular, right? And we can choose whatever point we want. It turns out if we choose this point I have drawn as a dot on my diagram, then the value of R that I use for these two torques is equal to 0. So if I choose this point, as my center of rotation, I'm going to kind of carry this in here. So for this point as my center of rotation, the R in my torque equation, the R for the normal force and the R for gravity are equal to 0 because these forces are not any distance away from that rotation point. They are at that rotation point. They are not acting to turn it one way or the other because they're going right through the center. So the effect of that is that these two torques in our equation just equal 0, which is huge because we don't know how big these are, and it turns out that doesn't even matter as long as we make this choice. So what we end up with is the following. We have our torque at point A plus our torque at point B plus some zeros, and we said before that the sum of our torques is equal to 0, so this equals 0. And now we're almost done because we can start plugging stuff in. So torque A is this force at point A, what we're trying to find, times this distance of 0.8 meters. Torque B is 294 newtons and 2 meters away. And relative to this rotation point, force B pushing that right end down, that is a clockwise rotation, and so this needs a minus sign. Can't forget about that. This plus this equals 0. And now we're basically done. We just need to solve for FA. So let's go ahead and do that. So 2 times 294 is 588. And so 0.8 times FA is equal to, if I move this to the other side, is equal to 588. So my force at point A is equal to 588 divided by 0.8, which I did not write down, but which is 700 and something. Dang. That's embarrassing, but that doesn't matter because we can still get the answer. So you guys can fill in the little math in the middle yourself. Because what we want is, we want FA, we know that FA is really mg, right? So this is ma times g. So if we plug in that this force from A is ma times g, what we get solving for ma is that it's equal to 588 divided by 0.8 divided by 9.8. And that I did write down. That is 75 kilograms. And that is our answer. Okay, so even if we had been given the mass of this board, if we had been given the mass of this board, we would have been able to figure out how big these forces are, but it still would not have affected this answer. So there is a nice way to get to that answer, even with these unknown pieces of information.